the average time to complete the Boston Marathon is 3 hours and 22 minutes with a standard deviation of 24 minutes. The average time to complete the London Marathon is 2 hours and 57 minutes with a standard deviation of 20 minutes. If someone completes both marathons, what time would you expect them to have? So this is like the time of the two like added together, basically. So we're going to take the 3 hours and 22 minutes and add that to the 2 hours and 57 minutes because we're looking for expected value. So this gives us 5 hours and 79 minutes. But 79 minutes can obviously convert to another hour with 19 minutes left over. So I'm going to actually call this 6 hours and 19 minutes. So this would be their expected time to complete both of them. Now, what is the standard deviation of the total time to complete both of them? So remember, we can't add standard deviations. Okay, so I can't just say 24 plus 20. So what I need to do is I need to square both of those, add them together, and then take the square root of that number. So I have 24 squared plus 20 squared, which is going to be, what is that? I know that one's 400. I don't know what the other one is. 24 squared.
576.
Beautiful. Thank you. So 976 total. So we're going to take the square root of 976. You know that one, Josh?
Nope.
Which is,
Oh, what?
that's half of it. 31.24 minutes.
Why do we square it first, like the numbers first?
Because you can't add standard deviations.
But you can.
You have to make them variances.
Don't you just love adding variance?
So then, on average, how much faster can a person run the London Marathon than the Boston Marathon? So, we have,
25 minutes.
yes?
What?
Because we have 3 hours and 22 minutes minus the 2 hours and 57 minutes. So that ends up being a difference of 25 minutes. Very curious as to what is so different that makes that the case. I don't know if one of them has like a lot of hills or.
Yeah, I was gonna say maybe one's like hilly, one's flat. Or maybe it's simply just like the people who run the race, you know?
Well, this is somebody that ran both. Like
Right.
this person ran both.
Right.
Every time I think of like a marathon, I think of the Boston one.
I know. Or ours
Yeah.
that's here. Just because it always messes up traffic
Yeah.
and how I get places. It's fine. All right, what is the standard deviation of this difference? So, it's actually going to end up being the same because we don't subtract, we always add, and so we're adding variances, and that's because everything's getting squared, so that's also why. So it's going to end up being the exact same. So we always add variances. Even when we are looking for the difference. So, still 31.24 minutes. All right, this next one, in a 4x100 medley relay event, 4 swimmers swim 100 yards. Usually it's meters, but okay. Each using a different stroke. A college team preparing for the conference championship looks at their times, or at the times their swimmers have posted and creates a model based on the following assumptions. The swimmers' performances are independent, and each swimmer's time follows a normal model. The mean and standard deviations of the times in seconds are shown below. So, what are the mean and standard deviations for the relay team's total time for this event? So, the mean, we literally just need to add them all up because it's the total time. So, mean is going to be 50.72 plus 55.51 plus 49.43 plus 44.91. And that's going to give us 200.57 seconds. Any ideas what I need to do to find the standard deviation?
Isn't it like the... Oh wait, never mind. That one is the other one.
So it gives us all their individual standard deviations.
Would it be like the like 0 plus things? Like, no, 1 plus 50.72 squared thing? We're like,
No.
okay. Yeah, I don't know that.
That's if we have the expected value. We have the mean here.
Okay.
We square each one
You laughing?
And do what?
and add them and then take the square root.
Yep, so we're going to take the square root of each of the standard deviations squared plus each other. So sometimes when I do this problem, I'll actually go through and square them and write the variances over here, but I'm not going to need the variances for anything else, so I'm not going to do it separate. So I'm just going to do 0.24 squared plus 0.22 squared plus 0.25 squared plus 0.21 squared. And when I do all that and take the square root, I get 0.46 seconds. All right, this next question is going to make us kind of combine some stuff from previous section that we've done this year. So it says the team's best time so far this season was 3 minutes, 19 seconds, and 48 milliseconds, I guess. I don't know. Anyways, that's 199.48 seconds. I like it that way better. Do you think the team is likely to swim faster than this at the conference championship? Explain. We are going to do it mathematically, but what do you think? Their best average time was 200.57 seconds.
So, no.
Or, well, their average time. Their best time was 199.48 seconds. Do you think that they will swim faster than their best time?
No.
See, you might know too much about swimming, so that might be why you're going to say yes. So, just statistically speaking, probably not. Because if that's the fastest you've done, you're probably not going to get much faster than that. However, in swimming, most people, when they go to compete at a level like that, where it's like a huge conference championship, they're swimming in a special suit that does make them faster. So, that's why I said you might know too much about swimming to be able to answer this question.
They never chose me for butterfly.
All right, so we need to find the z-score, which we haven't done in a while.
I forgot about those.
Me too.
So Z is, we take the amount of time that's like their best time and subtract off the mean and then divide it by the standard deviation. So 199.48 minus 200.57 over 0.46. And that's going to give us approximately negative 2.36. Now, they said something somewhere, I think, about assuming a normal model. Yeah. Each number time follow a normal model. So, normal model, their average time, 200.57. Then they've got this other time over here, 199.48. So I need to find the likelihood that they swim faster than that, which would mean less than essentially 199.48 seconds. So that's the area that's over on the left side that I need to look at. So we use a calculator function. Do you happen to remember which one it would be?
I know. Was it the thing with the random stuff, or was that something?
No, it was before that.
Oh, wait, I know it. Hold on. NCR. I know.
That's
it was
probability stuff.
It's not the second y equals stuff, is it?
No. Give you a hint. It's not the stat button. It's one of the other math things that we used a lot. Toward the right side.
Graph.
Oh,
What?
Graph. I don't think that's it.
I forgot.
How about normal CDF?
Oh, yeah.
What?
I remember that.
To the normal distribution, normal CDF, normal cumulative distribution. So you're gonna hit second VARS distribution, and it is option 2. So what you're gonna end up with in here is it's gonna be the -1 E99, which should be what your calculator's preset to. Then we're going up to actually, yeah, up to this. So they want it faster than their best time. So that would be 199.48. And then 0 and 1 are the mu and standard deviation that are already in there. And then you'll paste it and hit enter. Wait, I think I put the wrong number in. Hold on. I think I did this earlier on accident. What did I? Oh, yes, I did put the wrong number in here. We need the Z value going in here, not that number. This -2.36 goes in here. Knew I did something wrong because we've got to make it normal, and the Z score standardizes it, so that's where we need that. So that's -2.36. And when you do that, you should get 0.009 and so on and so forth. So do you think this team is likely to swim faster than this at the conference championship? No, it is unlikely. There's a less than 1% chance they will be faster. So assuming everything was exactly the same as it was all year, then most likely they are not going to. All right, the next one, and I normally skip 9, so we'll probably just do 8 on this one. Mr. Stames likes sugar in his hot tea. From experience, he needs between 8.5 and 9 grams of sugar in a cup of tea for the drink to taste right. While making his tea one morning, Mr. Stames adds 4 randomly selected packets of sugar. Suppose the amount of sugar in these packets allows for a normal distribution with a mean of 2.17 grams and a standard deviation of 0.08 grams. What is the probability that his tea tastes right? So, I know that the mean of each packet is 2.17, but how many does he put in there?
4
So, what do I need to do to find the mean for his cup of tea?
divided by, or,
There's 4 packets in there, each 2.17 grams.
oh,
So just multiply by 4.
yeah.
Yep, so the mean is going to be 4 times 2.17, which gives us 8.68. What about the standard deviation, though?
And, or do you, like, have to multiply it and then take the square root or something?
Or is it just like the square root of the mean?
Never the square root of the mean. Mean's
Oh,
always
okay.
something completely separate. Standard deviation, we need to take the standard deviation they gave us, and we need to square it to get variance. Multiply it by 4 for how many packets, then take the square root of all of that. So it'll end up being the square root of 4 times 0.08 squared, like that. Which happens to give us 0.16. So we know that 8.68 is the mean, so I'm going to look at my little distribution here. So I've got 8.68, but he wants it between 8.5 and 9. This is probably not drawn to scale. Well, I know it's not drawn to scale because that's not, it's more than 1 standard deviation away. But we're looking for this area in here. So I need to find my z-scores first. So we're going to do z equals x bar minus mu over the standard deviation. So 9 minus 8.68 over 0.16. And that gives us 2. And then I need to do it for 8.5. So z equals 8.5 minus 8.68 over 0.16. Which gives us negative 1.125. So now, just like the last problem, I need the normal CDF, but instead of the lower being like the negative 1E99 or the upper being that, because I'm in this intermediate range, I want the lower to be this one and the upper to be this one. So we're gonna have normal CDF of negative 1.125, 2, 0, and 1. And when we do this, we end up with .847. So basically, almost an 85% chance that his tea tastes right. So that's good. All right, so like I said, I'm going to skip this one. This is just kind of a weird problem, and I normally skip it because it's not really something you need to worry about. So I'm going to jump past that one. Plus, for the sake of time, getting all of this in. Oh wait, do we get out in 5 minutes? Gosh. Oh, we're not doing 11. Okay. We'll do this one tomorrow right at the start, and then y'all have whatever's left of time to work on this, and I'll give you your review questions tomorrow, and we'll do the quiz, test, whatever you want to call it, on Thursday. So y'all also have time on Wednesday if you need to as you look back over stuff. So we'll do example 10 tomorrow right at the start. Probably take us 5-10 minutes, and y'all should have the rest of the time.
Okay.